go through the second half of the course, the second half of Unit 5 somewhat quickly, so you get so you can begin working on the mechanics, because that just takes practice. And then we'll go through the theory during the first half of next week. Okay? All right. So I want to define something that we didn't quite use in the video. We didn't use this term in the video, and that is the term net area. And I want you to contrast that with total area. Okay, so sometimes we'll be talking about net area, sometimes we'll be talking about total area, but we're going to begin all of our discussions with net area. Okay? So first of all, let's just give an interpretation of what we mean by net area. So suppose we have this function right here, okay? And let's say we've got this function between a and b, okay? And so we want to talk about, well, how do we find the net area between the curve and the x-axis? Okay? So I want you to think about that word net just a little bit. Okay? And again, so if we talk about the total revenue of a company versus its net profits, okay, revenue would always just be a positive quantity. It's just money coming in, versus net, which is a difference between two things. Now, that's how I want you to think of that word net here. So we're going to develop a tool that's going to compute this area underneath these curves, but we need to know how it works. Okay, so we'll go through the specifics of this tool next time, but we'll see that our tool is going to count regions that are above the x-axis as positive quantities, and regions that are below the x-axis as a negative quantity. Okay? Now, if we want total area, what do we have to do? We just have to make sure that we break it up between the regions where it's positive and negative, and we just change the sign on the negative regions. Okay? But our tool that we developed calculates net area. Okay? And this is how we're going to express the net area underneath the curve. We're actually going to define the net area underneath the curve in section 5.2, but for right now, let's just talk about how we're going to express it. Okay, so we're going to say that the net area is given by this symbol right here. I want you to first think of this as an entire symbol. I think that it's very important that you realize what type of object this is. This symbol stands for the what? It stands for the net area underneath the curve, right? So what type of object should it be? Would you expect me to say it's the sine of x? That's the area underneath this curve is the sine of x?
It's the value.
It's a value. Specific. It's a finite value. It's a number. If it can be finite, yes. Good. It's a number. So it's important that you realize that this quantity right here is a number. Right? It might be the number 35. That is the area underneath the curve. It might be the number pi over 2. That's the area underneath the curve. But it's got to be a number. Okay, so this is the first thing you need to do, is recognize the difference between the indefinite integral that we introduced in the last chapter. Okay? I think it's always very important to separate when you learn indefinite integral with when you learn definite integral, so you can kind of classify them as two different objects. So we've already said this. This symbol looks very similar to what we wrote as our indefinite integral, but of course we're going to call this the definite integral. How do you distinguish between the two? Yeah, we've got this x equals a number and x equals a number in both the numerator, or both the top and the bottom of our integral symbol. Okay? So we've got that x equals a to x equals b. That's how you recognize, oh, I'm talking about a net area here, not an antiderivative. Now we use the same symbol because in a minute we're going to see that the calculations are similar. Okay, but I need you to distinguish between this versus this, which is an indefinite integral which returns a function, more specifically a family of functions. But if you want to just say it returns a function versus this returns a number. This is absolutely critical going forward at some point. Okay, so what I'm going to do then is jump to the main result of this section, which is the fundamental theorem of calculus. Okay, how important is something called the fundamental theorem of calculus? It's fundamental, right? Okay, this is going to be something that connects the two different big ideas: finding the area underneath the curve with the tool of differentiation, or specifically the tool of anti-differentiation. We're going to see a connection between the two. And we're going to spend some time exploring that because it's important to learn that intuitive connection between those two types of ideas. But for right now, I'm going to jump. In fact, we're going to skip the first half of the first half of the fundamental theorem of calculus and just give the second half, which is the most practical on a day-to-day computational level. Okay? So this is what it says. Okay? Suppose f is continuous, then if I ask you to find the area underneath the curve from x equals a to x equals b of f of x dx, if you want to compute the definite integral, if you want to find the net area of a region, you're going to do so by simply calculating capital F of b minus capital F of a, where what does capital F represent? And this part's a little bit tricky, we'll talk about this. Capital F of x is any antiderivative of f of x. It turns out that continuity is more than we need. We can relax that a little bit, but we're not going to worry about that at all.